Am I ready? I don't know. Who, you know, somebody really I didn't know you could move this thing up and down. Apparently you can. So somebody whoever was here before me must be a dwarf. I know, it's because I'm thinking of Game of Thrones, okay? Next.
Ooh, did you watch on Sunday?
Okay. This stuff, you know all about the neural plate. I've got a better shot of this. This is just good because it shows the day. So on day 24, the neural tube is closing. Remember, you've got an opening at the rostral end of the tube, one at the caudal end of the tube, and it comes together and it zips up, and those little bumps on the side are called somites. Somites are mesoderm. The tube itself is ectoderm. Yeah, there's a human brain, which is basically 1350 to 1400 cc's. Very complex, probably the most complex thing in the universe. Those are, you probably know all those anyway. Yeah, you do anyway, but we'll go through. You've got a central nervous system and a peripheral nervous system. Now, the important thing here is that we're going to be talking about the central nervous system, which is everything that's inside of your skull and everything that is inside of your vertebral column. The peripheral one is out there, and you can break up that into the somatic and the visceral. But the point here is we're talking about the central nervous system. That's what I want to hit here. These are the neurons, the function. Remember, you've got afferent neurons, which is the information coming in from the body. You have efferent neurons, which is the motor control going out to the body. So you've got one coming in afferent, one going out. So one you can say is somatic and one is motor. And it's basically like this. I mean, you've got a receptor in the blue, those are the afferent. So the information's coming in. And that little bump on the side of the blue that's sticking out, that's a dorsal root ganglion. We'll talk a little bit about that. But the information's coming in, it goes into the system within your brain or within the spinal cord. That's an intermediate, and then to go out is an effector, which is the afferent. Now, this is important because a lot of these things are what they call subcortical, meaning that what stops you from biting your tongue all the time is the minute you start to bite your tongue, there's a feedback loop that goes straight into the nerve and it goes right into the effector and blocks the muscles of your mastication, so you're not constantly biting your tongue. That's an important thing. If you do, or if you know somebody that bites their tongue all the time or bites their cheek all the time, you're not supposed to do that. That may mean there's a problem and have it looked into. You guys don't take neurophys, right? I mean, in neurophys, I gotta tell you, when I took neurophys, I was convinced I had more brain tumors than you can imagine. Because we all know every now and again you bite your tongue. And they tell you this, like, oh my God, I think I bit my tongue like yesterday. Oh, I'm dying. But don't worry about it. Everybody does it every now and again. Okay, incoming processes within the canal or within the brain, and then outgoing. So that's really what it's all about. Oh, do I want to go into this? Well, you should know, you've got a bipolar neuron, which is, you've got the cell body and one dendrite or one axion going out. You've got a multipolar, which is a very complex cell where you have the cell body and dendrites going out all over the place, and a pseudo unipolar, which looks, I think I have a picture. Yeah. The one I want you to know are the multi and the bi. The other one would be basically one of those nerves within the column. Glial, just know what glial cells are. Glial cells are the sheath that surrounds, oligodendrocytes. They're a sheath that surrounds, and they do it in a fashion, they circle it, and they surround the nerve itself, the axon, and what they do is it's a way to insulate. It insulates the electrical charge. It's very important because it really speeds up the electrical charge because you're not leaking from the synapse. I'm sure you already know this, but if you don't, if you cut something down the middle, that's a sagittal plane, right? Mid-sagittal, if it's off to the side, it's parasagittal. If you cut through it, perpendicular to that, where did that come from? I don't know. You go perpendicular to that, that's the transverse section. And the coronal section, this is the coronal suture right on the top of your head. And you cut through in that plane, that's a coronal suture. Now, what is this? I don't know where this came from. Let's go here.
No, don't put that.
I didn't mean to do, well, I did mean to do this. I'm sitting here talking about neurons and mine aren't synapsing very well. Touch anywhere to go back to main menu. I'm not touching anything. I knew it when I hear a voice go, no!
Just help it out.
It's kind of like, do you think this gun is loaded? No! Don't. What have I done? Identity hard. Stop them. Oh no.
We could just talk about this.
It's going to be a very short lecture. I never even got to the cemetery.
When do you think we're gonna run into that? What are the numbers? No, tell me the box.
Ectoderm from the roof of your mouth, which is ectoderm, and you get a pouch that comes up, and then from the diencephalon from the top, you get more ectoderm coming down, and that's why you have two lobes. You'll see. Maybe you won't. Now, I'm ready. Can I just do this? Okay. You guys got this. Yes, thank you, thank you. And this is the same thing, when you talk about the brain or the face or the head, the rostral end is your nose, your face, the back of it is the caudal end. And also this is important because your brain flexes, and when it flexes, you still have, you still can describe that as anterior and posterior. Yeah, that's a flexion. And that's why you can talk about a dorsal and a ventral to the brain, but because of that flexion, you would have, you can see what that does to the plane that you're describing. That's why. Rostral and caudal. Rostral top, caudal back, tail. That's a section through the cord, and that just shows you You know, once again, dorsal, ventral, left and right. And when you're looking at an MRI or you're looking at a CT, you gotta remember it's as though you're looking at the person's feet. Look, that's the section that you're looking at. I think I show you that. This is a, do you remember, that's gray, the little butterfly in the middle, that was the cell bodies. On the outside, with the gray matter, on the outside is the white matter. It stains differently, which is why it looks like that. And it also, the stuff on the outside is glia, that's the sheath that surrounds the nerve.
Dr.
I
Latimer,
think I've got, there we go.
Dr. Latimer, I have a question. So, when you're talking about the MRI and the CT, so when you say we're looking at the feet, do you mean we're looking from inferior to superior?
Okay, well, see this?
Yeah.
Those are pictures from a MRI or a CT, a scan.
Okay.
And when you look at that, imagine, you have to remember that what you're looking at is the scan as though you're sitting, looking at your patient's feet. So that's the view that you're getting. So, and remember, it's been mirror image, so that what is your left is right. And what's to, you know, so it's been switched. So you gotta remember that so you don't foul up looking at these things. That's a coronal view. How scary is that? It's a creepy way, I don't know, maybe just me. That's a sagittal section through the head. That's an axial view or a transverse view. Okay, we've all been through this, but remember the neural plate. In the neural plate, let's see, I think. Okay, you have the embryonic disc, which is starts out as a bilaminar plate, which is ectoderm and endoderm. Some of the ectoderm goes through that cleft, through the neural groove, and that turns into mesoderm. So that's what creates the trilaminar plate. So you've got the three tissue types. BMP, do you know what that is? Bone morphogenic protein? Okay, well, I'm not going to ask you about that. A bone morphogenic protein is an inducer. It's a gene that induces other tissues to do different things. So the BMP comes down, and the notochord is there, and the notochord is made up of mesoderm. But the important thing here is bone, the BMP signaling comes on and causes things to change. And what does it do? You guessed it. It makes neuroectoderm, which turns into, and those happen to be the antagonists, noggin and nodal. I'm just looking for, do you have any of this? Okay, well, I'm not going to go into it. You know what? You're lucky, because next year I have to. Because in the exams, they're going to start asking for genetics. Because it's became more and more important. But you guys, I'm not going to, I don't have to ask you this. You can thank your lucky stars. I think. All right, so you've got the notochord, then you end up with the neural plate, and neurulation is what happens when you take that ectoderm and you make the neural tube. Remember, it's all about flexing, and so here's the neural plate, there's the neural groove, and then it turns into the neural tube. And in the middle of the neural tube is the neural canal. And that's what, I'm afraid you can touch this thing now. On the bottom, that's what that hole is in the middle. And remember, the neural canal turns into the ventricles. And I'm not going to, since you guys are head people, I'm not going to worry about the secondary ventilation, which is the closing of the caudal tube. We're not worried about that. So I'm going to shoot through some of this pretty fast. This is all about the tail, the caudal tube, but it's the wrong end for you guys. That's the neural plate. And as you know, it starts You've got underneath the neural plate, you have the notochord, and it's the notochord that sends up the BMP that causes these things to start to happen. The paraxial mesoderm, that's what turns into the muscles and the skeleton on either side of the neural, but we don't care about that right now. Okay, it flexes, we know that, the groove turns into a tube, and lo and behold, what happens? Neural crest cells. And then the neural crest cells start to migrate through the body. They start out as epithelia. Epithelia do not travel. They're flat cells, and they have an adhesion. They stick to each other. These things have to delaminate, which is to say they change the polarity. Okay, it doesn't really matter. They change their polarity, which means that they can then travel around the body. And they go all over the place. And it's an interesting thing, is when they migrate and they delaminate and they go through that, do you know what else does that? Metastasizing cancer cells. They do the same thing. Because cancer cells should not migrate around, but they undergo this same thing, and very likely it's the bone. It's that BMP that may be triggering cancer cells to metastasize. So there we go, neurulation. There's the groove. And then it turns into a tube with the neural crest cells. And then it, they travel all over the place. That's a section through a early fetus. And you can see the neural tube surrounded in yellow, the somites that are on either side of the neural tube. And they start moving around. So it's the interesting thing, how they travel so far. And remember, they make things like melanocytes. So that is meaning that they have to get way out into your toes and your fingers in order to create pigment in your skin. And that's some of the stuff that they make, that NeuralCrest makes. Truly amazing. And this is just some of the stuff. I'm not, what you want to know is that, the peripheral nervous system is important, because in certain cases when NeuralCrest doesn't get to your gut, your enteric system, there's all kinds of really serious bad stuff happens. Have you talked about that kind of stuff? Celiac disease, all that kind of stuff? Yeah. So it won't be on the test. If you want to learn, by all means do. Neuroectoderm turns into all these things. The pineal glands, what I'm trying to get to. This is a 23-day-old embryo. You can see the top that the neural, so you've already fused the neural tube except for the rostral end that is out there that turns into the brain, and the caudal end down here that also turns in. We'll see what happens if that doesn't fuse. And those little bumps on either side, those are the somites. You have paraxial somites and mesaxial somites, and it doesn't matter. They turn into, one turns into bone, one turns into muscle. So there the forebrain is forming. Oh, look at those little bumps on the back of the forebrain. You know those are the pharyngeal arches. And there's a lot of stuff that goes wrong here. If you don't close it, you end up with neural tube defects. This is at the other end of what you're going to see. But you do get neural tube defects like this, where the caudal tube did not fuse properly, and you end up with the neural tissue coming out. If you break away that arch, this is what can happen. Spina bifida, there's a lot of people that have it, they don't even know, they usually don't know it's occulted, meaning they don't know. But the other guys are bad because the neural tissue is migrating because it's not held in by the bone because it didn't fuse properly, it migrates out. That's particularly bad, and it has to be surgically corrected if it can be. People normally don't walk, ever. And this is what it looks like, but again, it's on the wrong end of the body for you guys. This is a normal, you can see the neural tube coming down. Actually, if you talked about things like cauda equina in the medullary, it doesn't really matter, because I'm at the wrong end of the tube. That's what happens. You see that? Let me just back that up. That's the first lumbar, second, third, fourth, and fifth. You see that white line running down behind it? Well, that's the neural, that's your spinal cord, but it's really not your spinal cord proper. That's what's called cauda equina, because your spinal cord in the beginning is a fetus, runs from your head all the way to your tail. But then what happens is your vertebral column grows faster, and that means you stretch out those nerve roots, and it looks like a horse's tail, which is why it's called cauda equina. Well, you can see how thin cauda equina is there. Look how fat it is there, because it's getting pushed out. And people that have spina bifida occulta, for reasons I have no idea, very often have a tuft of hair at their lower back. That hair is ectoderm, which makes sense. Okay, I get that. But why hair? Why does it grow there? I don't know. No one's ever explained it. These are some of the horrible things. Yeah, we'll just skip that. Okay, on the other end, on the head end, this is the kind of stuff you guys are going to have to work with. This is lamina terminalis. That's where the anterior neuropore closes. And it normally, if it doesn't close properly, you can have issues there too. And that's this sort of thing, anencephaly, where the tube doesn't close properly and you end up with neural tissue coming out. And that's, horrible things. Anencephaly meaning no brain. Very sad. So, neuroectoderm. Okay, here we're going to talk about the tube itself. So you start out with the neural canal. You've got a ventricular layer that surrounds the canal. That forms neural tissue. In a chronological sense, then you have a marginal layer, it's glia, and then you have an intermediate layer between that. And this is what it forms. You guys I don't want you to know that. This is just the bone morphogenic protein versus sonic hedgehog. Those are two different kind of material. I know, geneticists have a sense of humor if you can even imagine such a thing. So the sonic hedgehog works against bone morphogenic protein, and there's a gradient, and that tells you what you develop into. So you got the BMPs, and you got the sonic hedgehog, and this is what you end up with. This is important. On the top, you've got the alar plates. The alar plates are afferent. They have impulses coming in. The basal plate on the bottom, on the ventral side, those are efferent. Those are the motor neurons that are going out. And you just want to remember here in the middle where they come together, that's called sulcus limitans, where you've got the afferent and the efferent that pinch together in the middle, And the black space there is the neural canal. Yeah. This is dorsal root ganglia. The dorsal root ganglia is a cell body immediately outside of the spinal cord, and the dorsal root ganglia, which happens to be neural crest too, those are where the afferent are coming in. They stop at the ganglia, and you get another synapse, and then it goes into the alar plate. And you can see the basal plate, the alar plate on the top, dorsal limitans is between them. You can also see the neural canal, gray versus the white. Okay, now over there on the side, that's the dorsal root ganglion. So you've got fibers, axons coming in from that, going into the dorsal horn. And then going out, you've got efferent. And the intermediate neurons that are inside of the horn. So there, once again, you can see it coming in, the receptors coming in. That's a little bump on the side, that's the dorsal root ganglion. It goes into the alar plate, it hits another nerve, a secondary nerve. That secondary nerve then triggers down to the effector. So you're constantly having a feedback loop. It's telling you, tells your body where it is, what it's doing, how to connect, how to contract a muscle, all those things. The very fact that you can, your proprioception, I mean, this is amazing. If you think about this, you can blindfold someone, or not even, you can take your hand and put it behind your back, and you know where that hand is. You can't see it, but you know that's proprioception. That's because this thing is exquisitely tuned to let you know where things are. And here's the neural tube. You in the cortex, you know, in the cortex of your brain, which is the telencephalon. You remember you got a prosencephalon. The prosencephalon then turns into the telencephalon and the diencephalon. Well, the telencephalon is what forms the cortex. That's the big piece of the brain that you see looking on the outside. That has 6 layers in it. All mammals have 6 layers in that. Birds don't, but who cares about birds? But all mammals have 6 layers, and they form a particular way. I'm not gonna. If you want to know about this, talk to me, and I could go into. I'd be happy to talk to you about this. But if I'm not going to test you on it, I don't want to clutter your brain. Unless you want to be cluttered. If you want to be cluttered, there's 6 layers of cortex. You've got axons that are shooting through this thing, and it starts at the basal membrane and has to work its way out through all these cells. It's kind of a neat process. But that's not what I'm trying to get to. Ooh, well, yeah, this is bad stuff. This is if the ventricles, meaning the neural canal, doesn't fuse properly. You have all kinds of problems, none of which are very good. Oof. This is only, that's the dorsal root ganglion, the DRG. So it's outside of the spinal cord itself. That's where the cell bodies are that go into the alar plate. You can see them going into the alar plate. I'm trying to think, where would that probably be? That's probably thoracic, upper thoracic. When you have an expansion. If you look at the cord, you have an expansion in your spinal cord, one of which is the cervical expansion, the other one is the lumbar expansion. And the reason they're expanded is because you've got more cells there, because the muscles that the efferent that are going down to your lower limb, expansion, and up here in your neck, you've got another one that goes out to the brachial plexus for your arms. Okay, you already know this, but at the top, you've got the alar plate and the basal plate. Alar is afferent, basal is efferent. That's what it looks like in real life. Okay, now on to the ventricles. That's what you're looking at here. We've opened it up. That's the fourth ventricle. And what happens is you expand the top plate, the dorsal plate, which forces the alar plates apart, and that's what gives it that sort of trapezoid shape in the ventricle. You can see where that, I mean, even at this point, you can see sulcus limitans. You can see that it's opening up like that butterfly. So you've gone from the neural canal, you've opened up the top of it, the roof of it, because it expands, and that creates the fourth ventricle that is down in the base of the brain, which is the pons and the medulla. And okay, here we go. You can see it starting to flex. So you've got a cervical flexure, which is down where the spinal cord meets the basal brain, the rhombencephalon, and a cervical and a cephalic flexure, which is where the forebrain meets the midbrain. So it's flexing. And this is what it looks like. It says 3 at 4. That means at 4 weeks you've got 3 ventricles. And the ventricles are the one in the prosencephalon, the one in the mesencephalon, and one in the rhombencephalon. If we move to the 5th week, you see that those flexures have occurred. It's expanded out laterally, and then you've got 5 different ventricles instead of 3. So you've got 2 lateral at the top, at the telencephalon. You drop down, you've got another one at the mesencephalon and one at the bottom. So basically what you've done is to take the neural tube and you just expand it out. And those are the ventricles. So these are the portions. The prosencephalon turns into, again, going rostral to caudal, the telencephalon and the diencephalon. The only thing I want you to know about the diencephalon is that it turns in, that's where we get the neural portion of the pituitary gland. Mesencephalon is easy, that stays the same. Rhombencephalon breaks into the metencephalon and the myelencephalon, and I think, yeah. And this is what they turn into. Telencephalon turns into the cerebral hemispheres, diencephalon to the thalamus and hypothalamus and the epithalamus. Mesencephalon is the midbrain, and then you get down to the basal brain, which is the pons, the cerebellum, and the medulla, which are, at the very, very bottom of the brain. And these are what, as it expands out like that and flexes, that's what forms the ventricles. And remember that all the ventricles are lined in what's called epidema, which are these cells that line it that have cilia. So they're moving, and they're constantly moving the CSF up and down the column. If those things are paralyzed, this is truly amazing. This is new. Nobody thought this. If they're paralyzed, you can get things like scoliosis. You can get terrible defects in the spinal cord, and as well as in the vertebra. That apparently seems to be what causes scoliosis. So once again, we're looking at, you go from 3 areas of the brain to, you separate those so you get 5 areas of the brain, and that's when the ventricles are formed. I'm trying to get, there we go, from a simple to a more complex. Okay, here we go with the ventricles. So as it expands out, as the telencephalon expands laterally, and remember that forms the cerebral cortex. you're pulling those lateral ventricles out to the side. They look like horns. So you've got the lateral ventricles, then you've got the middle ventricle. The middle ventricle is connected to the fourth ventricle by the aqueduct, the cerebral aqueduct. Now that aqueduct is important because it narrows down to a very, very fine little place. And the reason it doesn't expand is because that portion of the brain, the midbrain, doesn't really expand much at all. So if it can be occluded, and if it gets blocked, that cerebral aqueduct, if it gets blocked, that's when you end up with hydrocephaly. Which here just shows you how these things are, as the brain grows, the ventricles grow as well. And there's just a picture of what it actually looks like. That's a cerebral aqueduct right there, which connects the fourth to the third ventricle. You can see how narrow that is. And that's a transverse section through the brain. That would be the aqueduct. And you can see it's stenosed because you can't see. They've come together. And if that happens, you end up with hydrocephaly because the fluid, the CSF, can't get out. It then starts to expand the brain. The brain then expands the skull. But they can put in a shunt. That's what the shunt looks like. They can go in and drain that until, and you're normally fine. Yeah. That's, again, that's the, you've got the basal brain from the rhombencephalon. So you've got the cerebellum, you've got the medulla, you've got the pons. That's the very lowest part of your brain. The forebrain, which is the diencephalon and the telencephalon, I think. Telencephalon is the stuff you see. All the gyri, all the sulci. Diencephalon is that little piece there, just below the ventricle. Mesencephalon is the midbrain. And metencephalon is the basal brain, so that's the pons. And then the cerebellum, I think, is over there. Yeah, cerebellum is over there. Okay, here's what I was trying to get to. The pituitary gland, the hypophysis. The pituitary gland has two lobes, an anterior and a posterior lobe. The anterior lobe is sometimes called the adenohypophysis, and the posterior lobe is the neurohypophysis. Why did they call them that? Because of where they come from. And they're located in the sella turcica. Sella turcica is right in the middle of your brain. That's that little, it does look like a saddle, that little cleft in the sphenoid bone, and that's where the pituitary gland sits. I mean, you can imagine how difficult it is if you do have a pituitary tumor, which we'll talk about. How do you get to that? You can't go in from the top. It's impossible. You have to go through the nose. And as you go through the nose, to get to that thing, it's a very, very difficult operation. In fact, there's something called circle of Willis. Do you guys know about that? Okay, the circle of Willis is sitting right there. And your circle of Willis, you do not want to go in and nick that. If you nick the circle of Willis, it's good night, Irene. So it's a really difficult thing to do. There's a pituitary, that's where it sits in the cell. Okay. From the diencephalon, remember it's all ectoderm. From the diencephalon, you have an infundibulum, and then Rathke's pouch comes up from the bottom, which is the roof of your mouth. So there comes the stuff from the top, and it goes from the bottom, and they form the anterior and the posterior lobes of the pituitary. Now that stalk of Rathke's pouch normally obliterates, but in some cases it doesn't. In some cases you can end up with cysts that reside in there, and that can be a problem. You can actually end up with cysts in the back, when I say back, the far back of your pharynx, your oropharynx. So that's what it looks like. That's why you have two lobes, two different types of tissue. Well, the tissue's the same, but it comes from two different areas. The adeno comes from the bottom, the neurohypophysis comes from the top. They grow together and sit inside the cella turcica. And there you can see it, and you can actually see the two different lobes. Nope, not going there. And that's it. Now what I want you to know the pituitary. You're going to get hit with that for sure. Know, I know it's a pain, but know the different lobes of the brain when they start. So you start out with the pros, the forebrain, the middle brain, the hindbrain. The prosencephalon, the metencephalon, and the rhombencephalon. The midbrain stays the same, don't worry about it, but the front does not. The front then diverges into the diencephalon, which is where the pituitary comes from, and the telencephalon, which is what your cerebral cortex is. The back of it turns into the metencephalon and the myencephalon, which turns into the cerebellum and also into the pons and the pons in the medulla. Thank you. My medulla's not, well, that medulla doesn't help you except breathe. Which is why it's really bad if you get hydrocephaly and it forces your brain stem down through your brain and magnum. That's why you choke. You die because you can't breathe. If you want to know, that's why. So, that's basically it. Know about cerebrospinal fluid. Know about the choroid plexus, otherwise you'd have hydrocephaly all the time. So you're recycling this stuff all the time. You know that on the inside of the skull you can see the granular little pits in the skull. The arachnoid granulations, right? Okay, so that's where those things are sitting inside the dura. Oh yeah, know about the dura. Well, you already know about the dura, right? So you've got the 3 layers of dura. Know that the cerebrospinal fluid runs within the subarachnoid space. Okay, so I mean, that's basically what you got to know. So, Happy Easter! I want you to know, this is really the weirdest thing ever. The class before this, the students are giving presentations. One of the guys, and it has to be something on evolution, one of the guys gave his presentation today. Do you know what it was about? Rabies. Oh, now there's a nice thing to talk about for Easter. Anyway, rabbits get rabies. Rabbits